On free body diagrams, let me um, let me just sort of explain where I'm coming from on this and why some things are pretty have to be sort of set in stone on these. Your free body, like a free body diagram, is a diagram of a free body. I don't know if you've ever thought of it that way, but I'm here to expand your minds. That free body has to be something in two dimensions. You have to be able to draw a closed curve around your free body. And in 3D, you need to be able to draw, or there needs to be a closed surface around your free body. Okay, so like you need to be able to rip off your free body and totally enclose it in a bag or something, you know, something watertight. Okay, that's what a free body is. Closed surface. And that is why I want your free body diagrams to always be an outline with no details in it. So like in this example, okay, so I know this seems a little silly, like I'm gonna show you what the free body diagram looks like that you need for this, and then you need to resubmit it for the points. But I'm just trying to make sure that this message gets through because it's something really easy and it makes a big difference, especially in the points I give you, which is what you care about the most, I'm sure. That's a little messed up. Okay, so here is the outline of the free body that you need to isolate in this problem. Okay, you have the two pulleys and you have the whole mass thing. Think of this as like your, you have to be able to, you know, shrink wrap your free body in 2D or 3D. Okay, this is the outline of the shrink wrap that you're drawing. Okay, and drawing it this way is really useful because then you deal with the weight of the thing. There's the weight. And then you just go around the outside boundary looking for things that are touching it. Okay? There's a cable touching here, and so we have a force here, force, here, force, here, force. Okay? And that's all you have to do. If you don't draw that shrink wrapping, you draw details and cables and whatever, you start to get things like this, which are examples that I saw. So this was a pretty common thing. Just draw the whole, you know, draw the whole free body, draw everything in the free body. But now it's not totally clear whether this is a two-dimensional shape or a surface, okay? Whether this is internal or external, okay? So I had people doing things like they draw this and then they draw a force here and then a force here and a force here, maybe some forces here. Just kind of random forces that in some cases were internal to the body, some cases were external. It just really throws you off. And I saw this example too. Okay, so this is bad. Don't do that. A free body diagram. So once you calculated the tension in that cable, you had to calculate the force vector that was being applied to the wall. So I saw this, a new free body diagram that looked like, how did this look? Maybe there was a pulley involved here, okay? And so there's a, maybe like a force like that, a force like that. There's a wall here. Is that wall internal or external, And so I think you'll be surprised how much clearer it is in your own head when you start thinking of all your free body diagrams as like you break off a piece, shrink wrap it, draw the shrink wrap, okay? So that's what I want to see, not this, definitely.
So did we need a free body diagram of the wall then?
No, you didn't need one, but if you wanted to do a free body diagram of the wall, if you think about it as like you're trying to break off a piece and shrink wrap it, then it becomes clear that what you need is, so you do have the wall, right? But then also at some point you have to break that piece of the wall off from the rest of the wall, okay? That's what's made clear by this. And so you have a force here, but then you realize, oh, I have a fixed joint too between the wall here that's part of my free body and the rest of the wall that's not, right? And so where this side touches the rest of the wall, the fact that it's a fixed joint says you have to have, some force vector on the body by the wall and a couple on the body by the wall, okay? So that's, if you're going to draw, like, and don't do any halfway free body diagrams, pseudo free body diagrams, like either do a free body diagram or don't. You know what I mean? So if you're going to do a free body diagram of the piece of the wall, then this is what I want to see, okay?
So it's better not to just not do that free body.
Okay, so yeah, when do you have to do a free body diagram?
Because that's kind of confusing now.
When do you have to do one? You have to do one anytime you're going to use Newton's second law and or rotational Newton's second law, okay? In this case, this was an example where somebody was just using this as a picture to show the force direction, okay? So in that case, I guess that's sort of a gray area to me. I could go either way on that.
Can you make sure you go towards the giving us?
I'd be happy either way. I could be perfectly happy. But with this, I'm so unhappy. So yeah, and it's not just for me. This is a habit that you need to develop because it's a way to communicate with all the professors that you're going to have in the future, And the reason it's a good way to communicate with them is because it's a very clear way to, free body diagrams weren't just made by people who wanted to take off points on exams, like free body diagrams are super useful because they organize your thoughts and give you everything you need on the left side of Newton's second law, and then you just are left to think about the right side. Okay, so that's the big thing. I want to see an outline. Okay, this was another sort of borderline call that I'm gonna make the tough call on. Okay. Like, yeah, I could see allowing this as a diagram of a free body, but let's just go all the way and say always it has to be a closed outline, So just draw the little closed piece, I'm confident you can do it. Because you start getting, I don't want to beat this to death, but I've taught this class. This is the third time I've taught it. I taught it twice at the U. And I used to be more flexible on this. And what I see a lot of times is that people start to, there's a reason it's not called a free edge diagram or a free line diagram or something, you know. It's because you have to enclose material, you know. In 2D, that's a plane, a piece of a plane, and in 3D, that's an object with mass, you know. And when you put lines in there, it seems to make people confused in their own head about like what forces we're talking about, you know? Because in this case, maybe this cable, you're not applying anything to the sides or whatever. But if you look at this picture, it's easy to imagine this as a single edge. And if there's forces coming from both ways, maybe you could, this probably isn't the most perfect example of this, but you could draw like the forces coming over here, thinking of this as an edge, and neglect the forces over here. Or you could draw the forces over here, thinking of it as the other edge. You know what I mean? And that's just what I see happen. People get confused when they do that. So just make it very clear to yourself what's the body. And then all you have to do is include the weight and go around the boundary looking for forces. Okay? Any questions on that? Okay. So this time, redraw the free body diagram. And actually, if there was other stuff that went wrong on your homework, feel free to resubmit the whole thing, and I'll give you the points back. But I'd say for half the class or something, you got like things went well on the problem, but you got a 2 out of 3 because the free body diagram isn't the way I want to see them. So in that case, just staple a new free body diagram to it. I'll give you the point back. Okay. There's one more thing that I want to be very clear about on free body diagrams. Okay, so this is the first thing. The second thing is there are 2 ways to indicate load vectors. These load vectors are force vectors or couple vectors. And in 2D, those couple vectors we sort of think of as just, you know, moments applied like this. So this is how I draw those a lot of times. You can have a totally unknown vector in which case you draw something like this with an x component and a y component. That's how I do it, but it actually might be more common to see it like this. Okay, either one of those is fine with me. But either one of these indicate that you have a full set of components unknown for that vector. Okay. And you label that symbol with a vector value or a vector variable. So for example, you put the symbol here saying you have an unknown force vector, and you label it force, you know, A, B, with a vector symbol, okay? Or the only other way to label these, and you also could, you know, if you know these values, it could be something like that, right? The only other case that you could have is that you indicate you don't have a totally unknown vector. You have, or let's see, unknown might be the wrong way to describe this here because like this one is an unknown, but we're listing it as a, so sorry, let me just call this like a full vector. Or you have a vector where you indicate a direction, okay? So if you specify a direction, like that, okay? Like you know something about the direction of this load. Then you label it with a scalar value or a scalar variable, okay? For example, an arrow with a scalar t. You know, that comes up a lot because you know the direction of a force applied by a cable. I saw a lot of cases where people would draw a known direction and then label it with a, like this would be a t with a vector symbol over it, okay? Don't do that. Specifying a direction like this means that you only have a single unknown, right? Or you want to specify the vector, you only need to specify a single scalar value, okay? So any questions about that one? Does that make sense? So don't label arrows with variables with vector symbols, okay? Because that's sort of redundant.
I got one question
Yep.
kind of along the lines, not exactly here, but for the answer,
Mhm.
do you want it always in two-component vector form or three, depending on whatever? Or can we, like if it's 2D, can we just put so many newtons in a 45-degree angle?
Yeah, sure,
'Cause
you
I
can do
think
that.
like the book
Yeah.
does that.
Yeah,
sometimes.
either one of those is fine with me. I think most of the kind of problems that I write, it'll feel more natural to give it as vector components.
Okay.
You know.
Because I wrote it both ways on here.
Okay. Yeah, either one is, they're both fine. But if I ask for a force vector, you should always give me some way to specify the whole vector, you know, like in this case. So what was the answer? 250.
245.
245 arranged at like.
And then I just put a 45
Okay.
angle on it.
So that's fine, or negative 173, positive 173 is fine, or you know, depending on how your coordinate system is. But I asked for a vector, so don't just give it as 245. You know, that's not a vector answer. The other two are. You know what I mean? So that's stuff that I'm gonna be very black and white on in this class, because those are important things to do to communicate with other, you know, engineers, and honestly, like they're just useful things because they make people think that you're smart. You can trick people. Okay.
And then you said depending on your coordinate system, do you just like if we drew a wall and changed our coordinate system to a 45?
Someone did that.
Angle?
Yeah, somebody did that. Like I thought they had their answers. I thought they had their answers wrong, and then like had their answers switch signs, and then they had a coordinate system drawn, and that's great. I mean, that totally is fine.
Okay.
Be a little careful. Like with 2D, it's okay you can have your x going anywhere and your y anywhere perpendicular, but remember that these have to be, they're like cross product restrictions on your axes, you know, like the right hand rule x to y has to point your thumb in the direction of the z-axis. So in 2D, you can do anything because we don't draw the z-axis. Like this implies that the z-axis is into the page. You know what I mean? So don't. So yeah, be sure that if you're going to use some crazy coordinate system, make sure that it satisfies the right-hand rule. Okay. And if you don't know what that means, then don't be too crazy with your coordinate systems.
So then you're saying that's not right then?
This is right in 2D, but what wouldn't be right is
Well, okay, yeah.
in 3D.
Moments and stuff.
In 3D, if you went X, Y, Z, that's not an allowable coordinate system.
Okay.
Any other questions?
It'd be okay if you put a negative Z.
Yeah, I guess. I don't think I've ever seen that, but yeah, I guess that's true.
Do it on the next one.
Great. I'm looking forward to that.
It'll be challenging.
Yeah, I know. Okay, so last time, the exam I think the first exam is 2 weeks from today. Right, it's the 14th today, so. And last time we were talking about centroids. And we talked about how to use centroids to calculate the center of mass. There is another thing that we use centroids for. That's for distributed loads. So today we're going to get into that. So just as a little reminder of where we are, there are two uses for the centroid. I mean, there've got to be a million uses probably, but for us in this class, there's two uses. Like one use is you can put a flower there and it looks pretty. But that's not what we're doing in this class. You can, but you don't have to. The first one is finding the center of mass location. That's what we did last time. And remember that is true only for homogeneous bodies. Otherwise, you have the equivalent or similar formula that the total mass times the center of mass actually, no one uses that for center of mass, so I'll write it as capital X, capital Y, COM is equal to the integral over the whole mass of the location of the center of mass of your infinitesimal mass dm. And then that corresponds to, if to break it up into pieces, that corresponds to, this is m total. M total times x, y, center of mass is equal to the sum over all the individual pieces of the individual mass times the individual center of mass. Okay, that was a long reminder. And the second use is distributed loads. In a rigid body, and remember, a rigid body includes a free body while we're isolating it. Okay. A distributed load can always be replaced by a single force vector. By a single force vector. Where the magnitude of that single force vector is the area of the distributed load. And I'll do an example where this will be more clear. Distributed load. And the location of that single force vector is the centroid of the distributed load. Okay, so here's an example. Say that we have a cantilever beam connected to the wall. And a distributed load is being applied that looks like this. So all the forces are downward, and that's the only kind we're going to deal with in this class, although you could probably, once you get used to thinking about these distributed loads, I think you could probably figure out how to generalize this to distributed couples and distributed forces that are acting at angles and stuff. There's nothing too complicated about this, but these are by far the most common you'll have to ever deal with, and this is all we're going to do in this class. And this point here has a value of 5,000 newtons per meter. Okay, so that's how distributed loads are always going to be reported. And that means that given the length of this, let's say this is 1 meter long, you can, at any location along the length, figure out at that point what's the magnitude of the distributed load, right? Halfway up, it starts at 0 here, so halfway up would be 2,500 newtons per meter. All the way here is 0 newtons per meter, okay? And we want to figure out what are the reaction loads at the left end at the connection with the wall. So I'm going to draw a free body diagram. what do the loads look like at the wall? What do the reaction loads look like?
Full force and force.
That's right. So we have the force on the body by the wall and the couple on the body by the wall. And then this distributed load has a triangular shape. Where's the centroid of a right triangle? Do you remember that? I did an example last time where that came up.
1/3 from.
Yep, 1/3 from, so it's up 1/3 and it's 1/3 from both of the fat sides, right? So there's a force here with a magnitude that's equal to the area of this distributed load. So the area is base times height over 2, which is 5,000. So 5,000 newtons per meter times 1 meter divided by 2 is 2,500 newtons. And this distance is just 1/3 of a meter, right? And what about the location up and down? It doesn't matter in this case, that's right. Because you can, without changing the results that we're going to get from this calculation, you can move this force up and down along its line of action. Okay, so that's how it's always going to be. When we're calculating equivalent loads due to distributed loads, you're only going to have to calculate the horizontal location of it. The vertical one isn't going to affect the problem at all. Okay, because these loads are always vertical. It would be different if they had components. Okay, so that is a complete free body diagram. And now,
Oh, no weight or anything?
yeah, I'm neglecting it here. We'll assume that's just really light and the weight is negligible compared to that external force. So now we've reduced this to exactly the kind of problem we've been doing. So P, A, rho, F. We should come up with a little little mnemonic device to remember that, like prepubescent athletes, rho for mother. That's the first one that came to mind. Maybe you can come up with a better one. Okay, so we have to choose where the coordinate system is. Might as well choose here at the wall. So first, let's do this force on the body by the wall. So that's located at 0, 0. For an about point, let's choose 0, 0. So rho is 0. The force is F on the body by the wall, X and Y. And the moment is 0, because rho is 0. Then we have that couple. That's also located at the wall. None of these other ones are relevant. And that's the moment on the body by the wall. And then we just have this force, 2,500, okay, wait. So the location is 0.660, right? I could choose any y value I want. The about point is still zeros. So rho is 0.6670. What's the force vector?
2,500.
Negative 2,500 because it's down. And it's always going to be down. Negative 2,500. And then 2/3 of 2,500, you get negative 1,666.7. So then Newton's second law says add these up and they're equal to 0. FBWX, FBWY plus 0, negative 2,500 is equal to 0, 0. So the force on the body by the wall is equal to 0, positive 2,500 newtons. And the rotational equation says the moment on the body by the wall minus 1666.7 is equal to 0. So the couple applied by the wall is equal to 1666.7 newtons times meters. Yep.
How did you find the area of distributed load, that 2,500 newtons?
Yeah, it's always just the area of the distributed shape. So it's just the area of this triangle.
Okay.
Okay, so it has a length of 1 meter. I mean, obviously it's not drawn to scale in terms of those numbers, but it has a length of 1 meter, a height of 5,000. So it's just half base height.
Oh, that's the height of 5,000. Okay.
Right.
Okay.
Yep.
So you're more or less going to give us an equation for the distributed load then?
Well, you could come up with problems where you have to do an integral, but I think it's safe to say that on, oh boy. Yeah, probably there'll be at least a couple of practice problems where you'll have to do simple integrals, but most of the problems you're going to know the formulas or be able to look them up. And on an exam, like if I gave you a distributed load that was a triangle or let's see, the ones they have in the back are triangles, semicircles, and quarter circles, parts of parabolas. Any of those that they have in the back of the book, I'll just write on the exam. Okay. So that's about it. When you have a distributed load, you figure out how to resolve that into a finite number of force vectors, using this idea. And then you just do these problems the same way that we did the last set of problems, just rigid body, Newton's second law. Okay, so here's a problem for you to work on. Say that you have this object connected to the wall by a pin joint. And the object has this triangular shape. Okay, where the length of the shape is 1/2 meter. And obviously this would just swing down, right? So it has to be supported by some other kind of joint. So there's a cable connecting it to the ceiling. And there's a distributed load with a rectangular shape acting like this. And in a lot of cases, a load like this will just represent the weight of something lying flat across it, right? Like if you had a book lying all the way across this, a 1/2 meter long book, that's a big book, but then that's the profile of the load that you would get. Okay, and the question is, what are the reactions? So go ahead and work on that, work together on it, and
The force?
oh yes, 1,000 newtons per meter.
Does a triangular object weigh, you said?
Yes, thank you. 50 kilograms. Yeah, otherwise the fact that it's a triangle doesn't have any effect.
How tall is the triangle on the
That does not matter in this case because of the fact that you can slide forces along. Can you picture that?